And let's look at what we are covering last time, the slide, because I think that's easiest to see where we stop, because that will be somewhere we stop somewhere. Oh, I see. I think we just stop here. I think there's some typo in the slide. We just go back to this one. I think the tab is wrong. So otherwise, everything should go through. So let me go back from where the data is, and I download that part, and then we continue. So somewhere here, right? I just run cell and below, and then you should give us the graph we want. I mean, if you still remember, although it's a week, I hope you still remember what is the main point of the slide. Is somewhere in the middle is good, right? It's not something. Sorry, it should be the lecture. Should be the lecture 7. So it's not somewhere. Sorry, what is the? Yeah. So it is not the most complicated model, nor the most simplest model. Will do the job, right? I think we have talked about last time. I think it's up to here. I think this is a graph where we stop. Wow, sorry, just like scrolling like crazy. This is the graph where we try to plot, right? But we didn't plot successfully, but the time limit don't allow me to continue last time. That is the slides here. Is that slide there? So we success should be able to plot this guy, which show you that if you actually train the model using the full data, okay, the RMSE for sure would drop because of the fact that you increase more coefficient, then your model should fit better, right? But actually, when you put things in practice using test data, then it is like the U shape. Okay, you you should choose something in the middle, right? I think we have talked about what are the models are, right? And I think we just kind of stop at the part where we should use LISO for this one, right? We stop there, the LISO. And to do the LISO, okay, first thing to do, okay, there are many ways to do, but I've tried to modify the book. Is I would do a test train split, okay, and I train based on this the train data and split, okay, and there will be something there, okay. Although this is not the latest slide, I should have updated, but anyway, this slide works well. So what I do is a pass sy, okay. That why I'm not going to do that, because I want y and x separate, okay. And later you will see why I do that. I mean, and it's based on the most complicated model, right? Because what I want is I want the computer to pick the data among 300 variables there, right? So and the way this PET-C will do is you will not just a matrix, we call it design matrix. This come out somewhat like data frame, but it's not slightly but a bit more complicated. But anyway, this will store the column names. Okay, just a bunch of text there. And then I do the split. Okay, I use 20% of the data as the test. Okay, so this is the code. Okay, so I just split y and x based on the data. Okay, so that's, let me continue this one, do the copy. Okay, this is the code. Okay, I hope that become clear. Maybe I make 30%. I don't know which is the best, but 20, 25, I don't know, 25, 20, 20, 20 is fine. Okay, so then I split the data. Okay, and the next thing I do is to probably I forgot to mention is LISO, right? The standard way to do LISO is because I don't want it affected by the scale of x. So you would always do the standard scalar. Scalar means that you normalize data with mean 0 and variance 1. So basically you minus the column, every column, you subtract the mean and over the SD. Okay, that make everything is mean 0 and variance 1. Okay, and here the slightly complicated one is, okay, you would use the trained data to tell you what is the fit. Okay, so because the thing is, the trained data tells us the mean and the variance. You apply the same transformation to this one. Okay, let me draw a picture because that is a little bit crazy. Yeah? Okay, if you don't understand what's going on. So the data we have here, imagine this whole data. Okay, what we do is we take 20%. Okay, this part we call it test data, right? And this green part is the trained data, right? And the trained data is the one that we try to do the LISO to fit the model, and then later test the model based on the fitter one. Okay, so this is the one we run our algorithm, and then we test it. The problem is LISO, right? You have X, you want to normalize to 0 to 1, right? So basically, take all this data, look at each column of X, you subtract the mean and over the variance. So SD, right? Standard deviation, then become normalized. But you take this part and normalize, right? But what about this part? Do you normalize by themselves? No. What you do is, for each column X here, you remember the mean and standard deviation. You apply the same assumption here. Okay, you are not normalizing based on itself. You remember how you do it, you do it here. That is how you do in practice, right? Because when you have real data there, you impose the same transformation to that one. So that is how you want to do it, right? Because you transform the model, you apply the same thing there. So that's why you have the fit transform to let the Python remember how it fit, and you transform to apply the same. Okay, so that is a slightly little bit. I mean, when you see it the first time, you see, oh, what I'm doing. I mean, why I do something crazy, right? Why I don't just subtract the mean over SD and I'm done, right? Why I have to do this kind of stuff? Because that's the reason. Okay, and this is the train the scaled and test trail. Remember, we just scale X, not Y, right? Y is the same. We just normalized because the reason why I do that because the LISO is minimizing the sum of coefficient, right? So that's the reason. Okay, so to make sure that you understand what's going on, otherwise you will be a little bit curious what we are doing, all this crazy thing there, right? So this is the one. Oh, sorry, there's a comment there, but just keep that there. Okay, so we have the day. Now we have the date. Now we have scaled all the data. Okay, LISO, just to remind you, you will do that. Okay, actually, when you do regression, you do that. There's no difference. Just to remind you, because linear regression, you do this has actually no impact. Okay, there's no difference whether you do this or not. Okay, but for LISO, you do it because the fact that you are minimizing the sum of the coefficients. Okay, so next, what we do is I will use the LISO function to fit. Okay, and I will tell them what's the alpha or the lambda, right? The coefficient. Remember this alpha is how big you punish the size of the coefficient. Okay, remember this alpha. Go back to the very top. Sorry, we are just because we're reviewing. Remember alpha is this guy. Sorry, just go up all the way here. Okay, remember the alpha. Right? Remember LISO was doing, to recall, is minimizing two parts. The first part is sum of square error, which is regression part. This next part is the alpha times this absolute value, right? Remember, alpha is 0, same as standard regression. When alpha is super large, then for sure this will be 0 because coefficient will be shrink to almost to 0. Okay, and alpha is between 0 to infinity, right? Depends on how complex the model you want, right? The higher the alpha, the more simple the model you want, right? So alpha is controlling the complexity. Okay, if alpha is very small, then you allow the full model, right? If alpha is very large, then you reduce to a very simple model. So to work on it, oh, sorry, I go back to the very end of the slide. I'm sorry about moving around. And the LISO, okay, I will set alpha to 4. You can set to other number. I set it high because I want to make my slide more compact. So you can set whatever alpha you like because there's no, for the moment, there's no hard and fast what the alpha is. This is a taste of complexity of parameter. Okay, you like alpha big or alpha small? I don't know. Up to you. Okay, but you fit it. Remember, I use the X scaled. Okay, not the train. Okay, and this is done. Actually, if you do this, I'm done. Okay, this slide is very simple. So what is left here? Okay, is I'm trying to print out the outcome. Okay, and what I'm going to do is I will try to print out the coefficient that if I run to 2 decimal places, if not 0, I include them. Okay, so I just, you can, of course, you decide what you consider 0, right? But that would be the idea. Okay, so that's why non-null coefficient, because it cannot be exactly 0. Okay, so this is how no, we produce that guy. Sorry, I forgot this one. Okay, and then once you run it, you will see this the LISO our friend comes out very nicely. Okay, so this is the thing. Okay, they will do the LISO coefficient is once you run this object, right? This object, the coefficient is there, right? The features are the name that we named, and they will give you this guy. Okay, because I make alpha is very big, so that's why very little left, right? So suppose I just use 1, okay, not 11, but 1, then you have more, right? So suppose you want to be, say, don't want to be so crazy, maybe 0.5, then you have even more, right? So you have a bunch of stuff, right? Or you can even relax like 3, okay? You can relax a little bit here, okay? Then you have 187 column. So it depends on what you consider 0, what you consider alpha is the 2 control that you think that's relevant. Okay, is that clear? Okay, so now your lies right. The good thing is this is automatic, right? You just control this, the computer tells you what is relevant, what not. Okay, that's a LISO. And once you have that, then usually we want to do a plot. Okay, the LISO usually is we will do this kind of horizontal bar plot. Okay, so what you do is bar H. Okay, it's horizontal bar, and you plot what they are and plot this, and then you put the names. Okay, so that is how we're going to do that. Not going to explain line by line for this one. It should be, we have do this for 7 class already, so I hope this is not something that you feel comfortable with what we have already right now. So looks crazy, right? The reason of this crazy graph is because we have alpha is a little bit too small, so just make our life easier. I mean, to make it 4, then maybe make it 2. So we just ignore those 2 small coefficient. Then once we plot, this is something manageable. Okay, at least we can see. Of course, you can change, but you can see these are important coefficients, right? As we expect number of beds is important. How many people accommodate square? This is how large is the room is important, right? And whether private room is also important, right? And whether you're heating, internet, right? With the kitchen, smoke, interestingly, smoke detector is important. I guess people are afraid of the fire. Washer, wireless internet, right? These are all important for the model. Okay. So, but I mean, without actually looking at data, you don't really know, right? But now you know from the data tell us these are important switches, right? Suppose you are the guy who want to rent out your own apartment for Airbnb, then you should consider, right? Include washer, right? Include the internet, wireless one, heating, and other things, right? To be there to improve your rent, right? There's something that is in the model there. Okay, this is the graph. Okay, and the next thing is to look at RMSE, right? If you remember, the RMSE is like 40 something, right? Let's see this LISO, how much we get the reduction. Okay, and to do it, we do the mean square error and take a square root. So what I do is I predict based on a LISO model, right? And I do the mean square error, right? Or you can do the NP dot sum of the different square, the same thing, right? You can do the same because you have two lists of number, and that was the easiest way to do. But the many way to do it. But let's just copy that and see how LISO help us. Okay, and let's see why it doesn't work. Let's see this one. Mm-hmm. I don't know what's the problem at the moment. X has 300 features, but LISO expecting features output. Oh, I see. Is it the reason? No. Should be YX, should be right. I'll check out why it is not working, but it should give you something 30 something. But so once I figure out why this is wrong, there may be some article. I'll update the latest version, this will work. Okay. So the final one I want to mention is so far we allow the alpha to be chosen by you, okay? And one of the other way to figure out it is why don't we use the cost validation to tell us what is the best alpha? Okay, we choose the alpha based on 5-fold series. Okay, so what we're going to do is you give me what are the possible number of alpha from almost 0 to 4. Okay, and then we use LISO series, okay, to fit in all possible alphas, okay, and let the model train what is the right answer. Okay, so the funny part is you have to reduce the dimension of this y, okay, to make it work. Okay, so this one I figure out why this is wrong, but for the moment, let's assume we're here. So this is how you would do. Instead of LISO, you do LISO CV. Means that instead of single alpha, you alpha run from 0.05 to 4. So we'll figure out what's the best alpha based on data tells you. So the data tells you the complexity. So we have trained all this stuff here. Okay. Okay, you train many models very quickly, right? And then what you do is to do the same. Okay, this will give you the best model. Okay, I just copy this guy. Okay, and there are many alpha is possible, right? Based on this, actually train alpha different value. Okay, and for different value of alpha, you fit the model. You have RMSE, right? Then figure out the best one, and the best one actually give you by here, right? This is the one that actually gives you the best model. Okay, and okay, so this one gives you all the LISO coefficient, and this one gives you the non-null version. So you can see doing this using the LISO, you reduce the number of rows from 300 to 71. Okay, originally you have 300 something, LISO reduced to 71. Okay, and of course you probably don't care about what the model is, right? But what you probably care is first here is to give you what are the good coefficient, right? What's the best coefficient there? Okay, this is to look at the top 10 coefficient, right? Because that is something we care, right? There's 71, so you can't really solve everything. So I group the top 10, okay, and then I plot the top 10. So I'm not going to explain this line of code, but I think that is rather intuitive. Okay, so this will give you the top 10 coefficient, which is the most important thing, right? From the most important is how many people you have, what's the room, and all this. Okay, you can look one by one. Okay, how bathroom, so on and so forth. Okay, but of course, I guess the most important is look at each alpha. What is RMES, right? Look at how it looks like. Okay, and this one will tell you RMSE path means for every possible alpha, right? You look at the RMSE. Okay, so this one will give you the RMSE. Okay, and if you remember, actually the model performed pretty well because look at all the RMSEs below 40, right? If you still remember, if you run regression, the RMSE is at least 40. So if you remember, we go back to here, we somewhere stop, right? The best is model 7 is 39. Okay, if you allow start from the model 8, it's 40.8. We do a LISO, it's actually better than model 7. Okay, and more importantly, okay, this is the one here. We can find the best. This is the best one. Okay. Okay, we saw the best fit. Okay, best alpha. Okay, I mean, of course, we can look at what's the best alpha first. Okay, what's the best alpha? Let's see. So what's the best alpha we have? So let's see how complex the model is. The best alpha is 0.7. So the best alpha. And what is the best alpha? The RMSE is 37, right? So actually can go as low as 37, right? So you drop from the best case in our model 7 is 39. Now it becomes 37. So 10% drop, right? So even better than the best model you can from your head, right? So 37. Okay. So that would be telling us how you would improve your fit. Okay. And of course, you can do the y hat plot, which give this one. I'm not going to repeat it because you can just copy it, right? And you can combine the graph. I'm not going to do it again, but this shows this graph, right? The worst model is 42, and then you can keep increasing. Of course, it gets better and better, but it's 7 and 8 actually more complex model goes up, right? This idea say U-shape, right? And if you based on regression, you pick model 7, right? But if you use LISO, actually you have big improvement, right? A 10% drop, right? So that is the one of the most interesting use case, right? Because you have a lot of variable, you don't know which to pick. LISO help you, right? But of course, if you have 5 variable, then LISO has no use, right? Unless you have a lot of interaction and you don't know which to pick, then may still generate something. But in general, only you have like this kind of model, then you can go on. But as I said, your IT manager, your data you do is always usually have too many to handle, because website keep track of every single action of the guy who visit your website, right? Or you are looking at IT data like the e-commerce platform data or all the website data. So many things to control. And the problem is to pick up which one's relevant. And if you know what's going on, you're expert, then you know which to pick, right? But usually the case, you have no idea, okay? And then LISO is the one that help you to pick which one. I said, okay, I don't want to spend too much time on LISO because I want to go to most exciting thing is our regression tree and random forest. Okay, so in case I think you can run all this code without any problem, right? So if you have no further question, allow me to jump to this one a little bit before we have a break, because I want to highlight what is going on for this class, because I think we have to finish this one. Okay. So what we're going to do in the upcoming 2 hours, we'll be looking at regression tree and random forest, which will cover each of them in single 1 hour. Okay, 1 hour for regression tree. The other is random forest. Okay, but before we go, let's tell you what we're doing. Okay, what we're doing. So regression tree, okay, without, I'm not going to detail right now, but I just tell you what we are doing. Say, a typical regression tree is like this. Okay, suppose I want to predict y based on x. Okay, maybe I draw a picture, it's easier. Okay, maybe that would help. Okay, so remember, it's what, just a simplest case, single variable, y and x. Okay, so imagine we have a scatter plot. All right, and data here, I don't know, somewhere here, maybe somewhere here, I don't know, just some random thing, I don't know what's going on, but okay, this is the case. Okay, clearly, if you look at this one, you try to run a linear regression, that will be very bad fit, likely, right? Maybe if you're fitting a polynomial, maybe okay, right? But how many polynomial you can go? Maybe, right? Where you should stop, right? And you have to decide what is a polynomial, but then you have more than one variable, right? Then multidimensional, then how many interaction you want. That is very difficult. Okay, so regression tree is the way that you don't have to worry about how to fit the polynomial. Okay, we are trying to machine tell us how we do it. Okay, we don't have to decide the polynomial size. The machine will try to do it. How do we do this polynomial? The idea is like the following. Okay, we're going to do something very simple idea. Actually, it's very similar to the idea we have the bin scatter plot. If you remember what's bin scatter plot, is to, before we do, we separate x into different components, right? Remember what we do, right? bean can support is okay. Okay, this is one bean, this is one bean, this other bean, right? And the way we do the bean is, okay, we decide what is the right grouping, and then the prediction will be the average within this will be my answer, right? Right, this is the idea, right? This group by X, and then there's a prediction, right? That is what we have, okay? Now, we have to decide how many groups we want, and then try to draw lines and then try to fit the best, right? That's human, okay? We want machine learning, so let the machine tell me how to do the grouping, okay? And the way we do is by what we call the tree idea is progressively optimized, or in computation, it's a greedy algorithm. Instead of global minimization, we try to do it step by step, okay? So we don't think about at the end, we just walk step by step, 见一步走一步, okay? So how do we do that? So first, what we're going to do is, tree is like we're doing every time we do a bisection, okay? We cut into two halves every time, okay? So the first thing to do is we are trying to consider a model, okay, that I cut into two halves that would minimize my MSE. So what I'm going to say is, suppose what I want is, suppose I cut it here, okay? Then this model will say, okay, average of Y is here within this, which was the color, right? Look at this part, okay? The model is predicted here, all right? I do a spin scatter plot. If the model is here, my thing is here, right? Maybe lower, right? So for this, I can calculate MSE, right? For each part, right? And by moving the pink line, I would allow myself different grouping. I'll choose the best line that separate them such that my MSE is the lowest. This is my first step. So every step I look at how I move my needle to make this prediction error measured by MSE is lowest. Okay. Now the next part comes in is, once we did that, we want to continue. Okay. But now assume, because we do step by step, so the orange is one well now. Okay. Look at the orange. Now we consider whether we want to do some cutting. Right. We will look at maybe I want to cut, what color I should have? Blue. Maybe I cut here. Right? Then the model here, we keep this guy and kill this guy. Right? Then I keep moving the blue, okay, so that to minimize MSE within this region. I do the same to the other side. Okay. I will do the same for the other one. I will do the cut as well. Maybe somewhere here, somewhere there, right? Another one, I look at, move it around to make the MSE lowest. Okay. I keep doing this, then I'm done. Because you can see it's a nonlinear shape right there. Right? It's a you can say it's automatic bin scatter plot based on MSE. The machine will learn by doing that. Okay. But of course, here I choose one variable, but you can see if you're two variable, the same thing, right? Because you just pick the cutting such that the MS is lowest. Okay. You do one cut every time. Okay. So that would be the way that to handle. This is actually regression tree, right? And you can look at this particular example here, which I will go into more detail, but okay. This tree, I look at the case, the data is like this one, 1, 2, 3, 4, 5. The prediction is 2, 4, 5, 4, 5. Okay. And then we'll look at whether X is more than 1.5, they give you the other tree. And this gives me here. And here I tell later I will do more deep is you control how deep your tree to be. Okay. You will do 1 level, 2 level, 3 level, 4 level. And then you can decide how deep the tree is. Okay. And there are many other rules that you can tell how big the tree want to grow, how when to stop, but this is the basic idea, right? It's basically a automatic bin scatter plot. Okay, you automatic group them, and then the prediction is the average between the group. Okay, basically just cut to group them into a nice form, and then you're done. Okay? And in the example we just saw, right, it's nonlinear, right? Because that is very similar to the case where if you ever do the model, right, you run the regression nonlinear, it'll be something like this as well, right? You will fit this one. But this one is, if you fit the black one, you have to think how many polynomials you want to fit. Okay, what x squared, x cubed, x to the power 4, 5, when to stop? We don't know. Okay, but this one you don't need to think. Okay, just tell me how complicated model you want, how many depth you want, and you're done. Okay, the maximum depth, then you tell. Okay, they will stop. Okay. So that is something a little bit better because we don't need to think in advance how nonlinear you want, right? Because before you have to figure out how to fit the model, but now we don't have to worry about that part. Okay. So this is regression tree. Okay. And probably you see the tree, then later we go after in the second hour, we will actually do what we call random forest. Okay, random forest, as probably you might know, is not a tree. It's a forest. It's many trees, right? But basically, is you are combining different tree, okay, and the average outcome of those tree will give you the random forest. You render a pick. The reason why is the problem of the tree is a greedy algorithm, which you don't optimize over the whole thing, right? Because every time you just look at which cut is the best, right? Every single point of time, then you may do worse. And it really depends on what data you're drawing on, right? So that means that you with random forest is you randomly go the tree and you combine the outcome of different random tree. That is the random forest. That's the idea. Okay? It's related to what we call the wisdom of crowds, right? 3个臭皮匠, right? 3个诸葛亮, so that's the idea. Okay, so that would be the idea there. I mean, you just that's how we will be randomly picking m variable and average those, because there are many things you can do, but you will just do that. Okay, but that will be covering after the break. So what we do is we have done the regression, we know very well, and we have just done LISO, right? LISO is you give all the variable, you tell me the functional form is linear, then you just machine pick the variable. And the machine learning is slightly a little bit more complicated, right? Right, because here the LISO can still allow functional form, right? It's square, whatever form you want, right? You pick the best model here. But the machine learning is even more simple. I don't need to worry about functional form. Just tell me what the variable, tell me how complex you are, and click, come out. All right. So it's no brain, right? But the thing is it good or bad? I don't know. I mean, it really depends on the outcome, right? Because in this one, human has no intervention. So a lot of domain knowledge, you know how well it works, cannot really input in the machine learning, right? If you know historically how it works out, then you can include it in the functional form, right? But you can't really word nicely machine learning there. Because machine learning is just like black box. You don't know what happened. Okay, this is the outcome, and that's it. Okay, you can't really go further, and it's difficult to do hypothesis testing, right? It's only can do prediction, right? And it's not. It's useful in prediction sense, but if you want to understand how scope, why it's the case, why the meaning is hard. Okay, it's for prediction you can use machine learning, but of course. That being said, right, machine learning can guide us like LISO, how we can construct regression, right? Because when you see this, then probably you want to fit nonlinear formula, right? So that would help a little bit. Okay, so I guess I talk too much. So I think it's good time. You can let me know what's going on there, and then we can take a break. So let me open the Q&A section. Okay, and then we'll resume at 3:35. Okay, go around to see if you have a question. Please fill in if you have some question or query or concern, because this is effectively the last class for exam, right? The next class will be, we cover something that is important, but we are not putting the exam. Okay, but I'm not saying the next class is not important. Next class is also very important, but just not in the exam. Okay. 马上中院会10万亿的，中院已经想好10万亿的是货币政策的大方向。对，中间这段时候本来上周指标就会10万亿出来的，等到这个大手出来就可能股票会猛涨。对啊，大家已经想好了，就是大方向。没有川普大方向，因为川普提高非常多的关系，和中国不需要大方向。怎么讲？短期肯定是，但是长期短期肯定是其实不算涨。再讲了，我不知道，大方向。当然我没有办法，没有去，我说我可以讲，没有办法，我没有跟大家去买，因为这个还是这个你不要把它像那种生不是每一个都讲。对啊。今天马戏跟网上面，对吧？所以买美股比较简单，肯定会取证。对，马上就要肯定买起，美股可以，美股买起，美股都买不起，可能不要玩。回家去试试。对。我不炒了。我不炒不等于我家没人炒，家别人炒，就负责不用炒，我就负责 save。有一个人 take risk 好人，太多 take risk 坏人，太多坏人。对，家里面每个人都在炒股票的话，就是万一不行了就完蛋了。对。怕什么？炒了。对，他影响我做研究教授，我一炒就是什么都不记得了，什么不想干的。对啊，就是心情会一个太过 fluctuate， 所以就还是上课时间超不行。OK， 好，输有一个快速先用2千60个个手。有被动投资就是退休金的过程。好的。买很多美国的股票。比快递。Who do I support? Obvious, right? Look at my smiley face and you know who I'm supporting. If I'm a sad face, you know I'm supporting who. Yeah. Can you repeat what happened next class? Okay. Next class we'll cover the last 2 lessons in a little bit brief way. I'm not going to go over too detail about the Python code, but I give you idea what's going on when we do causal analysis. Just give you some idea. But we'll probably not go over the Python code next class, but because we finish everything, try to finish everything, random forest and regression tree today. And I'll upload the past year paper. I should have done that Many times I do it, I forget. I will try to do that. Actually, do it. Then you see what is there. Deadline for group project, I think is the deadline is when you submit the you present, right? I think you are presenting on 20, right? I think I read that down, right? What's the deadline? I think I read that down in the project guideline, do I? I think I did. Let me check. I think on the very last week of the class, right? The end of this month. End of the month. It's after the exam. Yeah, I think at the exam, right? On the exam day. Right? Very last day. 11月31吗？哦，30吧 ，then it's 30. Last day, last 30. 10月几号没有 ？Okay. Thanks for reminding. Otherwise, you never submit. Right? It's the very last day of the week. But do remember, you just don't over. Just remember only one side of the A4 paper. So if you have one person, just one page. Okay, 2 person, 2 page. So you don't write a lot. Okay. And make sure that your report is readable. Okay. Although one page, you don't force your font to be size of 8 to there. Right? Use standard font size 10, 11, or 12. Doesn't matter, but doesn't matter. I mean, but just don't make it too cram, right? I mean, it's business report, right? So don't cram everything there. Okay. What else? Tom or Harris? Yeah, you know my choice, right? But I don't want to I don't want to say it out because you know it. Okay. Yeah. Anyway, one candidate, if he win, you'll be more fun, right? The other one may be more boring. So you want more entertaining outcome. Anyway. Oh, cloudy. Yes, that's good. The speed is okay, I guess. Okay, overall is okay. Yeah. I mean, this is fun, yeah. I mean, it's a good one. So, yeah. Make ITM great again. I did predict, I mean, it's hard, well, it's no point to say it, but I did predict Trump win in the beginning. So, I make a wrong guess in 2020, but I predict him winning in the very early 2016, but democracy or republic? According to the Constitution, U.S. is not democracy; it's constitutional republic because it's a United States. So each state is democracy, but the whole thing is a republic. So it's slightly different from that, right? You have Senate, you have a legislature. There's a two-part, right? Yeah, I hope the world is good to you. Hopefully you guys will be happy, but I think it should be fine for my class. I'm not sure your Java, but my class should be fine. What will happen next? As an economist, I would predict tariff will goes up, and Chinese government will print money, a lot of money, so the stock price will temporarily boost out, and there are a lot of subsidy goes on, and there are more trade wars go on, and then inflation in US, and yeah, that will be a lot of things will happen, and then I think renminbi will depreciate because of printing a lot of money. So and then there will probably a lot of tourists come to Hong Kong because well, because of Hong Kong become more important when under the trade war. That is my prediction, but I don't have a model. I didn't run a model. That's from economists, so maybe I'm wrong. I mean, but there's no history to study, right? So it's hard. Well, if I have crystal ball, then probably I'm not here, right? Right. But that would be my prediction. So hopefully, I don't know right or wrong, but hopefully, it'll be entertaining outcome according to Elon Musk what he said, right? I don't know what's going on, but the most entertaining outcome is the most possible. That's what he said. So hopefully, a lot of fun will go on for us, and hopefully, at least the job market will be better for you guys. Well, it can't be worse, right? So anything change should be better. So finger crossed for you guys. So now, I mean, I think we review already the machine learning. What is machine learning, right? So the machine will select models and pick up what are the model that will be picked there. Okay, the machine will actually figure out what are possible models and select the right model. So different from LISO, right? LISO is still the model is like you fix a set of model, right? You just like which variable to include, right? But here it's like the model will actually given by that. Okay. So as we see, that will be the procedure in the machine learning that we have seen already. Just basically you have whole outset, right? The training data, right? And then you will do k times on training. That's the k-fold estimate, k-fold validation. And then you look at the best MSE average out, and then we estimate, right? This is the one we have been doing, right? That's called the k-fold estimate, k-fold validation, right? And as we said, we'll focus on these two. One is the CAT, or CAT, sorry, CAT. The other one is RF, right? Random forest. So we do the first one. Will be series of binary decision. As I said, cut. Okay. Now, indeed, that is actually we said, right? We basically cut it into different bins and average of value of these bins with our prediction, right? We said it already. Okay. And as we said, this is a similar to this, but bins are determined by machine through a step-by-step procedure. Okay. And there are some terminology I want to talk because as many of you will do machine learning the next semester, as I said, my class cannot do justice of big machine learning. Just I only scratch the surface, so that when you go to the next semester, when you learn machine learning, you know what's going on, right? Not completely blank. What to know? What is it? But now you have some idea what's going on there, and if when you're free time, you can look around what's going on. But you will learn, okay? And it's a tree, so we start from the beginning. The top node is the beginning where you start the cut, and terminal at the end. Okay, and sometimes called terminal called the buckets. Okay, and stopping rule is because the data is huge. If you grow the tree, then it can be very big tree. The data is large, right? So there will be some time you should stop fitting. The idea is same as what we do the LISO regression, right? That's always good to usually a U-shaped curve there. You don't want to be too complex, don't want to be too simple. You should stop somewhere, right? Because the RMSE will go down, right? And then go up again. Then you have to stop somewhere, right? So that's the stopping rule. And later we'll define what stopping rule. Don't worry, that will be something very simple. And branches is from the tree, you go from the look, you just go down to the branches, right? And cutoff point is when we stop, right? So that's really the stopping rule. And size of tree will be just how many split you do. So this terminology is nothing to learn here, but just name. Okay, I just put it there in case later we'll see. Okay. So how trees and cut are created. So cut actually provide you the rules, but there's no formula coefficient. Okay, but just the tree tell you what it is. Okay, bunch of rules. Okay, as we said, what we do is we look at all possible cutoffs and look at each cutoff, look at the RMSE, look at the lowest and do the cutoff. We had already said already, right? You see the graph, right? In case you forget, remember this diagram, right? That's we have been doing very clearly, right? Just look the cut of this purple line, look at the RMSE and the sequence cutting. Okay, so let us do the example as we do, as we see, right? So let's forget about this technical. Okay, so this is the package we use. We will do the machine learning doc tree. This is the tree package, and we will do the decision tree regressor, which is the tree line, and then we will do the matplotlib. That's not important. X is just 3 variables, and Y will be just 5 numbers. Okay, 1 variable, 1, 2, 3, 4, 5. Y is like this, and very interestingly, Python require you to be a list in each one. Okay, so that's why I do it. But don't worry about it because you usually have the data there. Okay, and then you just fit the tree, and then you tell him only one level. Okay, and this is the tree, and I want to plot it, and I want, because usual plot is small, I want it to be bigger. So I tell the figure size is 10 by 8. Okay, and then I plot the tree using the plot tree function. There, I plot the tree, put the name called X, and I fill the thing and put a title, and so it's very simple, right? There's nothing very complicated. But let's run it, because I think now after that, go back home tonight in your CV, you can run regression tree now. Okay, so this is a new skill acquired, right? In your CV, done. You got the achievement, right? It's a tree. Okay, CRT, right? Regression tree, and then the first one. Okay, now you can draw this tree. So now you have this tree as you see, right? So the thing look like this, right? You have 5 of a sample. The average is 4. Look at MS is 1.2, and then you get 1.5. So you just divide the data into less than 1.5, bigger than 1.5. So look at the data here. So less than 1.5, remember the data is, we have 1, 2, 3, 4, 5. So less than 1.5 actually cut here, right? So basically on the left-hand side only have one value, which is 2, right? Because there's only one variable, one observation, the square error is 0, right? Because exactly only one number. And here we have another one, we have remaining 4, right? And then the average is 4.5, the 4 sample there, right? So basically it's what you do, right? The model is the following. It gives me your X, okay? Your X is more than 1.5. The tree tells us you're here. My prediction is 4. Is that clear? If you give me number is 0, I will give you the left-hand side. My prediction is 2. Is that clear what we're doing? Okay. So, but do know that the interesting part is the machine tells us how you split this two. Okay, automatic, right? Once the data there, boom, right? So that's why it's no-brainer, right? Everyone, even the kindergarten kid, can press and this comes out, right? So that's very simple. Now the next part would be this is the model, right? And this is the prediction, right? You input 5 possible X, and then you ask the regression sheet to predict. It should give you this 4 number, because 0.5 should go to this side, right? And give you 2. 3.5 bigger than this one, you go to this side, right? Give you 4.5. 4.5 also this one, go to the right hand side, right? So that is how the let me copy this guy and then run this. Okay. Okay. So this is exactly what we have seen. So this is the tree, right? It's very simple, right? There's no model there, right? Just a tree, there's a rule there, right? There's no estimation of anything, right? Just divide a group. Okay. Now, I guess it's good to go back to the car case, if you remember, right? The car model. You have a website, there's secondhand car, right? And to see how the price is being done there when we estimate a model there. Now we're trying to do it is now go to regression tree. Okay, how to do that? So remember this data. If you still remember, if not, they just copy and paste here. Okay. To save time, I'm going to be fast here because I guess by now your copy and paste must be better than I do, right? Because I think you do a lot of copy and paste these days, right? From the ChatGPT or other software, right? And the next is I don't think we need to handle the missing data. Just go skip this one. We go focus on Chicago. So this person I focus on Chicago. Do the same reduction of data, okay? And how I handle missing because I want to drop something is crazy, right? So that's is the part we also did as well. Okay, this code had been up here last time already, so I'm not going to line by line and explain. But basically, what we do is try to remove observation that the price doesn't seem to be right. Okay, it's unreasonable. Okay. And how do we do it? Is do it full EDA, right? Look at data, look at this number, do they make sense? If not, then just drop, okay? Once we did that, we create dummy variable, right? And we have condition that have type condition, so we create dummy for this. I think this is something we have done last time as well. So I'm not going to be explain this part. In case you want me, let me know, but I just save our time, okay? And this is the last thing we do, I think. The cylinder is how many cylinder for this okay. So what left for us is to create a square term, right? Cubic term, and then I think we are ready to run the regression. Okay. I think we're ready to start our job as a tree. Okay. First is we would drop because we want to predict price. So look at the price that's not NA, we keep it and we set the index. Okay. So there's nothing new because when data is not there, then I don't think we need to worry about the model, right? Because that is what we are trying to do, right? If there's no price, then what are we doing? This is the thing. Okay. So now we are ready to do the right thing. Okay. So I forgot the test string split. I forgot the one line. I forgot it. Good. I have to put the test string split there. I forgot. How can I forget that? Let's copy the code. I'm too lazy to do this one. I don't want to type. Just being lazy. Sorry for copy and paste, but hopefully you can see how I do copy and paste, right? BF train, BF test. So this, I should have included this part, sorry. And I just, but by now you should know what we're doing, right? We just split the test string, okay? And the next part is to apply the regression tree, decision tree. X is the age, DF is price, because we learned that age is the best prediction of the price, right? We learned it for the last one, right? So this is a regression model. Okay. And we run this whole part, okay, which is to fit the model. Okay. So do note that there are some tricky part here is you have to, because X within a matrix, so you have to put another square bracket. Otherwise, it doesn't run. Okay. Okay, with the regression tree. So what we left is want to plot it out. Okay, this is the plot. Why I have the same thing? Okay, sorry. Okay, so that I plot the tree, we have done it, you just see. Okay, so the model become like this, right? Instead of regression, it's just a very simple thing is look at the age is less than 6.5 year. Your prediction, the price will be this price, right? $13,000. If your age is old enough, your model gives you $4,000. Very simple model, right? And this is different than regression, right? Regression will tell you for each age, the price can be different. But this, the simplest tree model, actually is very simple. Just ask yourself, is age old or not old, right? Where the cutoff is 6.5. If young, this is the price. Old, this is the one, right? This is a very simple model, right? Even simpler than regression, right? Regression actually gives you a linear line, right? But here is even more simpler. Is that okay? The first one, right? This is the first model, and then you know how to run the model. And right, this is the model we have. And of course, we want to do the plotting. Okay, so what we're going to do is to plot this result. Okay, and because this is basically a bin scatter plot, right? Because it's just divided into 7.5, right? So I will plot that. I just look at the minimum of the age or maximum age. I cut it each increment by 0.05. Okay, and then I predict the y based on the tree, okay, for every value of x. Okay, and I want to plot it. So this is the all possible ages I want to plot. Okay, why I want to do that later you will see because I want to put a line. That this one smaller will look nicer. Okay. Okay, this I want to put a line. This is the x and y. Okay, and then what's left is I want to plot the scatter plot. The first line is original data. Okay, and the second one is the one I just created. It's a line x predict and y predict. Okay, and others are just basically decoration, right? So by now we should be comfortable with this thing, right? It's not something terribly bad. Okay. So once we're done, sorry, this price. Okay. Once you're done, then you should be seeing this is the model, right? It's just like before 7.5. Look at this data. This is average here. Look at this is this, right? This is because this is just bin scatter plot. But the bin 7.5 is picked by machine, not your choice, not what you think is good. Machine tell what's good. Okay, so that's machine learning, right? Machine learn what is the good one. Okay, you don't tell what is the cutoff, right? Because the bin scatter is you tell what is the cutoff, but now the machine tell the cutoff. Okay, is that okay? This is the one. Okay, now we allow one level is very stupid, just because just left and right. But let us now have more fun to say 2. Okay, you can see the same thing, increase of 2, right? So I just quickly plot it because I don't want to spend too much time on copy and paste because this is too boring for every one of us, right? So here you can see the figures like this. Maybe I make it bigger figure. So this is a little bit too small. Let me do the plot size. It's much larger. Hopefully this one will help us make it bigger. Okay, if you put this one, you make a much nicer graph, right? All right, so you will be looking at this. Still, you can see I allow two level. It's still the same. The first cut, 6.5, and then ask whether it's less than 4.5 or it's just less than 13.5, right? And you can go down, right? It will basically give you 4 different outcome, right? Basically, you cut this into 4 different bins. Okay. Right. You can plot this out, but I'm not going to worry about the plot, but this is something how you should do, right? That become the model. Okay. So I hope it's clear what we are doing. Okay. And you can plot the model, and then this will become like this. I'm not going to work it out, but you can copy and paste, right? It become a 4 different group. You can plot this out. It's like this kind of plot is going on there. Okay. So just to remind you, machine learning is the machine is learning where to put the cut. Okay. The next is what we want is to compare how the regression model related to regression tree. Okay. And then with the test and train split 20%. So as a preview, you can see RAS perform RMSE is 2,300. If you use 1 tree, the RMSE is 2,500. But 2 tree already dominate ORS. So in that sense, okay, tree is better, right? Although tree has no meaning, right? Why you have this tree, there's no reason. But for prediction, even I have very simple this tree is very better, right? But let us really work out, okay? So the same here, we do the test string split, okay? We now have X and Y, okay? We split that out. Okay. So this I split out X and Y, right? So we run 2 model, okay? We do ORS, okay? And the thing we do, because we are running a compare model, actually we will use what we call the model that use actually prediction. So much faster is to use this learning library linear model linear regression. So what we do is we go OS the regression and fit the model and do the prediction and calculate the MSE and then calculate the RMSE. Okay, so that is the regression model there. Okay, so this is the OS model. So the whole thing is just regression model, we regress price on age, and I should print out the thing, right? Maybe I should look at the answer, right? Because this is not fun enough, right? Because I want to check it out, right? Because I want to look at what's the number. The number, as I said, is 2,300, right? Or S. And now, so I look at the outcome of the tree. Okay, the same thing, right? Just replace the linear regression with the tree. I tell them the depth of run, right? So do the same, the prediction, test them, right? There's nothing special here. Okay. And I want to print out this one as well, right? Look at how the 1 level tree goes on. I didn't define the train. Oh, Y should be a small letter, sorry. Typo, sorry. So 1 level tree is the 2,900. Okay. So OS is better than a single split. Okay. But now we are looking at 2 split here. Okay. The same thing we do we do first tree, right? Why I have so many duplicated slides? I'm so sorry about that. You can look at the tree looks like. I just, okay. Hey, this is tree. I think we know already what the tree looks like. 6.5, right? This is the fun we have seen. And we want to fit the depth of tree with 2. Okay. And we want to look at how it works out. Okay. And look at RM SE3 too. Okay. And this is 2,100, right? So which is better than ORS, which is 2,300, right? So in that case, 3 actually reduce the 10% of the regression error, which is remarkable, right? Because 10% improvement doesn't sound a lot, but if you think about improvement and just based on new model, actually it's pretty good. Okay. And now what we want to do, right? We've done everything here, right? Here's comparator table. I mean, I don't need to do it, but if you do that, it just gives you the outcome I have just said, right? If you do that, you can include this one. You will just give you the this result, right? Tell you that different part, right? 3 actually, the 1 tree is not so good, but 2 trees are good. Okay, so that's why OS is easy to interpret, but it's not the best for prediction, right? At least for this case, right? Look at the RMSE, right? Remember, already do validation, right? So now what is left is to consider the following, right? So far, we only have price and age. What happened if more stuff there, right? And is it going to be regression tree is better, right? The problem is because you have to pick what's going on first, right? And you have to decide which go first, right? You will do it sequentially, okay? And see whether the cutoff, okay? And which cutoff is reduction, RMS is the lowest, then the one you pick, right? So you start from variable 1, see which cutoff lowest RMSE. Variable 2, do the same. 3 and 4 and 5 up to n. And you do the first cut based on the first RMS is lowest. Okay. So what we're going to do is we go into the most complicated model, which is the model, which is age, odometer, LE, XLE, blah, 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 blah. Okay. And then what we're going to do is get the model there. Okay. First is the feature part is this is y, right? I want to get the x. So instead of 1, 0 is if you get 0, it will be this guy. 1 will be all this guy, right? And strip means I forget about the space. And because of the separated by plus, I use the split plus to get you the list of the features, right? Age, comma, da, 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 right? And then the feature name will be just, for each feature, I just drop the name there, okay? I get the name. Okay. A bunch of name there. Okay, now just do that. Something like that. Okay. Once I have that, then we can continue. Okay. What I'm going to do is I use the history matrix, right? What I do is based on the model, I take out X and Y and here. Okay. That is how I do it. Okay. And I do a regression tree with level 3. Okay. Then I want to see how this model looks like. Predict the tree here. Then next thing is to do is to plot them, right? There's nothing very special here, but just plot them. It's too small, so I need to make it bigger, see if this helps. Change this guy. Still not enough. Maybe 12. 15, maybe bigger. Slightly better. Can see something, right? So first look at the odometer, right? And then look LE, look at odometer again, and so on and so forth, right? So that would be the, and then this is cut into these different pieces, right? So this is a 3-level regression tree, okay? And there's a tree here, okay? So of course, you need not stop at the depth with 4-level, right? 3-level. So it's more fun, right? Usually you want to have, say, 5 or more. Then once you do that, you can see the tree can grow like but it take a longer time. But the tree look like this, very complicated one, right? And of course, you actually don't care about this number, right? You care about the RMSE, right? Is it predict better or not, right? But that would be the way that you would handle it, right? So a remark that what we want to say now is, well, so complicated. So how are we going to handle this problem? Okay. So the thing is, there are 2 issues here. Okay. First is, of course, the tree is smaller, is more simple, much faster to run, right? Actually, see, 5-level already takes some time to run. Okay. So there will be 2 ways to make it stop. First is what we call minimum sample in this node. The idea is the following, right? Remember, let's just show the code. Okay. Remember when we run this, we'll tell you how many samples here, right? So what we said is the split we want to do, we make sure that the split, after the split, the sample size cannot be too low, right? Because when you look at the very beginning example, right, we allow ourselves, of course, the data is very limited, right? We allow ourselves something like crazy like this. I have 1 on the one side, 4 on another, right? 1 probably is not really meaningful, right? So we don't allow it to cut it to too small. So we have some restriction on the number of sample at the end of the node. Okay, this will be controlled by a Python switch. Okay, and the other one is called impurity threshold, means that you only want to cut if the MSE reduce certain amount, right? If you cut, you don't reduce, then you don't want to cut, right? Simple model is better. So you don't cut, you have to reduce, you have to make it, the measurement error have to reduce sufficient. That's a called impurity threshold. Okay. And let's do this first, and I talk about the CP later. So how do we do that? Very simple. Just to tell them, I want the minimum samples split 20 means that I want each node at least have 20. Okay, if not, then forget about it. The other one is called the minimum impurity decrease. You want the MSE to be reduced by the square error with this one, right? If not reduction, then I'm not going to do it. Okay, you can fit the model, the same thing, and then I'm not going to copy and paste because to save time, right? You know, you can copy it, right? At this moment of time, just become a much simpler model. Okay, and this is how you would make the model manageable, right? Because when you have a lot of data, then we're tempting to have a very big tree. Okay. And the last one is the splitting is not robust because it really depends on how you cut, right? And that means that I would grow the tree and cut it down and grow again. There's some algorithm behind, okay? But simply means I have a parameter called CP, okay? And which I control capacity means that if the model too complex, there's a cost of doing it. So if that's the case, I want to cut it. Okay, it's not very clear what it's doing because it requires some math. Okay. Oh, I don't know why I'm missing here. I should. I will put that back. Sorry, for some reason it's not there, and they will. If the CP anyway, I'll be there. I'll supplement the next class with that. But there's a way to control the CP. Why it's not there? Anyway, for some reason it's missing. I mean, I will make sure it's not missing next time. But that would be the. Oh, it's here. So what I plot is they call it CCP alpha. Okay? By changing this number, you can adjust the complexity. And sorry, that's it. Okay, I'll put them back. There's some issue with this slide. Sorry. Okay. So that will be how we do the model. Okay. And one thing that I want to mention a little bit, but I don't want to go into too detail because you will do in machine learning class. The good thing is I want to introduce the regression tree to you. But there's this one thing we call variable importance. Okay, just very briefly. There's a model to formally estimate that, but the idea is like how important is it's a variable, because so far we have looked at the tree, right? But we don't know which model is important. Right? It can be very complicated model. I don't know which one is important, right? So I don't want to know how important is this, right? The idea is if, okay, if I use this model in the beginning, right? How it's going to improvement, and then basically, okay, I'm not going to go into detail about that, but this is just Python code telling you somehow which variable is important. And you rank it, and you can see the odometer and age, which is the nominal age. This is the real age, right? Because how long you have driven the car, right, is the most important. The dealer and so on and so forth. These are the prediction, right? So this actually help us to see which is important in the prediction. Okay, and there's some way to calculate. I don't want to go over it because when you learn machine learning class, they will be there, right? Because I don't think you want to I talk too much about machine learning, which you will learn later. But actually, you can create a model, okay, and the feature importance. I think you need a package. I'll try to see if I'm missing the package, and then you can actually run this and plot this like this. Okay, I think we need you need a package here. I forgot to include a line, but I'll try to update that part. I don't know why this slide is not perfect, but okay. But let me finish the tree. Okay, as I said, we just scratched the surface. I mean, you spend the whole semester to learn all the machine learning model in the next one if you care. So, but I don't want to. So the good thing is, I like this slide because I'm in happy face. Okay, so you don't need to specify the full model. So that's good, right? Just let it put everything there. Just let the machine tell you which one is relevant, right? Like the LISO, right? And the difference between LISO and the tree is LISO is at least everything there. The adjustment, the program just tell you which one to kick out, right? So that means bottom up, right? So it's the right, it's bottom up approach. But this is top down, right? You start from nothing. You tell me which one to cut, which one to cut, which one to cut. You increment, right? Step by step, you make the model more complex by growing a tree, right? LISO is that you tell me the full model and cut, right? But regression tree is that tell me there, I just pick, right? So it's just the building approach. Okay. And the good thing is, I don't need to worry about the thing. I don't need to do EDA. Just put that in there, right? Just forget about EDA, right? I don't need to explore data, look at scatter plot, everything. Forget about it. Simple. Click one button, comes out, right? But of course, something is so good. If they're so good, we should have learned it at the beginning, right? Why we learn it here? There's some drawback. First, when your data has some extreme value, then you die, right? Because you just pick up, machine can learn, right? But machine don't know whether data is reliable or not, right? If data is some outlier, then your machine will just very stupid, right? And it's a black box. So why is split in this way? I don't know. There's no reason. You can't explain, can't tell people. What do we learn from this? Okay. Even if you say, even you have this variable importance, right? You say, okay, this is important, the other is not. Then you still can't say too much, right? Because this is just saying predicting better, right? And you don't really know, right? Why it's split in this way? I have no idea, right? But that being said, right? You have this in your pocket now, right? You can run the tree, do a prediction, can do your homework, and also do your project, right? The homework will be released later. When I finish the random forest, right? And then I put the code there. Okay. I haven't set the assignment yet, so don't worry. Probably next week I will release it. But I hope that's okay. And after the break, this is the comparison in the book, but I don't think we need it. I already said it already. Okay. If you want, you can look at around. And this is the model. Look at RMSE model. Okay. And you will see with the tree actually is better than is not better than the best OS model. Right. The best OS model is pretty good. Okay. But of course, this is not the best regression tree model, right? But at least it will just tell you that at least they are better than the linear version, right? If you are smart enough to think about polynomial, then this is not a bad choice, right? I mean, you start from the beginning, you look at this, how it looks like. It gives you some benchmark, how well your model is doing. Okay. So I guess we just stop here, the break of 50 minutes, and we come back to the very last important model for our class. It's called the random forest. In case you want to fill in things, please do so, because I want to know whether you have something question to ask here. If you want, you can leave the comment here. We will resume at 4:40. Hi, hi, hi. Let's see. Very happy. Because I know the result, I'm right. No, nothing. Oh, I think the answer is, I think they just look at the news is the Israel just fired their defense head of the Department of Defense, right? Who is opposing the full war. So basically what I guess is if Trump actually win, there will be a big fighting between Israel and Iran before Trump get into power. Because Trump actually told them that if you want to fight, fight before I get in the job. So there will be a big war go on and then end. Okay, that would be my prediction. So that's my view. Yeah, I think they will be like this. I hope I answer your question. Yeah, regression tree, I think everyone knows how to run it. And some of you actually asked me, do we learn the algorithm to do it? Actually, we discussed the algorithm already, right? Although we didn't give mathematically, the algorithm to run regression trees like this, right, is to go over everything, find a cutoff, and repeat everything and do the cutoff and keep doing this, right? If you look at the machine learning textbook, they just put everything in the math in this one. So I didn't do it because I guess you don't benefit from looking at the math, right? Because already there, right? And also the algorithm is already freely available online, right? So I just keep everything in the verbal term. But as I mean, at least some of you will go to the machine learning class, so I just leave in that class to talk about in more detail, because I then talk about how to implement this complexity, CCP alpha, those kind of stuff, right? But this just give you how to run the code, and that's important, right? Do remember our class, like the master program, we can't 1 year, we can't teach you everything, right? That is something impossible, right? So we just teach you the most basic thing. Then if you want, then you can go further, right? Because you know the idea, why we are doing that, and then that's how we learn, right? Because no matter how many things I teach you, there's something I miss, right? So that's always have to choose something. It's just the first class in economics, trade-off. We do this and we can't do that, right? So, but I'm very happy this year. I think this year I teach a little bit much better than last year. But of course, there are still a lot of room for improvement, as you can see. But at least I will think you're lucky than last year, because I think my slides, everything are better. So next year will be even better, okay? But of course, don't worry, because my video teaching still always in the YouTube. So even after next year, if you can see next year's class, you can see last year class on YouTube. Yeah. So if you want, you can go to last year, because right, you can check out my YouTube channel, right? In case you don't know, you can YouTube. You can take last year class already. You can look at my name. It's sorry. I have this is this year. I do have many years stuff there. So everything actually go back to my teaching in my Singapore. But the playlist you can check out. Why so many crazy things goes on? It's DOTE, DSME. The channel? Oh, just my name. That's my name. And then this is the last year teaching. You can check this last year. The slide is not as good as this year. So, but you can check everything is there. So in case, but the video for this class already in the blackboard. So in case you graduate from this next year, if I teach this class, then you can also watch the video again. Okay. So you can keep improving. Maybe after, if I still in this school, if I still allowed to upload, it will be all there. From this 10 years later, you can still check. So don't worry. I mean, you only can get better, right? When you teach, you keep improving. So go back to this one. Okay. Random forest is a model that, as you expect, tree is one thing. Forest means many trees, right? So it's what we call the ensemble method. It's combine different stuff. Right? Ensemble means 合唱团, right? It's combining different things combined together, right? So combine different things, right? It's combination of different wisdom. So combining different models, okay? So there is the following. There's two different methods. It's called backing and boosting, okay? So first, what we do is we create, okay? This is a little bit abstract. I don't go into detail, but I just give you the idea what we're doing, okay? In the random forest, why we can grow many trees? Because I would create k different data set, use bootstrapping method. You remember bootstrapping, right? Just original data, you create new data, right? You create a fake universe, right? And different universe, you feed a tree, and you combine different tree. That's very simple. Is that clear? Let me repeat. Your original data, you create k different universe using bootstrapping. Each universe, you feed a tree. You combine different tree. That's it. But of course, what is the meaning? I don't know, right? You just create k different world and feed a tree in this one world and average out the outcome. Yeah, well, so what? But that is what it is doing, right? And boosting is similar, okay? But you would be growing the tree sequentially. So in one universe, you have a tree, okay, go one a tree, and look at the other universe, whether you want to grow, continue to go the tree, okay? You grow one tree and grow the other, okay? So you would be keep growing a tree. So that's what I mean. So you have a data, you bootstrap k different universe, pick the first universe, grow a tree. The second universe, continue to growing the tree. Third universe, keep growing. Of course, you will cut out something, but you keep growing the same tree, but you have k different tree increasing different sizes, and that will be the average aggregate. Is that clear? So one is separate, one is sequential, okay? But as I said, I don't want to go into too deep, but there's a two different way in the literature that they do the method, okay? So let's see the random forest, okay? There's a special case of bagging, which is independent. So first you create k different data set using bootstrapping method. Okay, k is your decision, how many universes you want to create. And each data set, you grow a tree, which we have seen already, right? RMSE, cut, right? But the difference is because you do bootstrapping, so that means that the different universe, the data is different. That depends on how luck you are drawing. And then what you're going to do, you will be picking m variable out of what you want, which is randomly pick m variable and go to tree. But otherwise, if you don't randomly pick, then you go to tree is very similar. So they may be in the first universe, you pick the first 5 variable. And the next universe will pick some other 5 variable. So very different variable, and later you combine. Okay? And of course, avoid overfitting, then you would just randomly selecting variable is very important. But otherwise, you would just, because you do bootstrapping, right? It's like creating artificial universe. So you make fitting something is is not there. So that's why you have to randomly select m variable. Okay? And if you want to know the exact algorithm, you can Google it, but I don't want to go to detail because it's a black box anyway. You know more detail, black box actually no help anyway, right? Just know what's going on, then let the Python do the job and then you're done, right? You don't really worry about, if you know even more better, you're not going to change any of them, right? Just know the high level what's going on there, that's enough, right? Because it's a black box, so you can't see what's going on there anyway, right? So the only thing that probably matters to you is the tuning parameter. Okay. In general, random forest, you would grow 500 tree, right? That means that you create 5 different universe. Each universe will create 1 tree, and you have to tell you the how many variable for each one to pick, right? Because each universe you pick a variable, and the standard one is square root of n. Okay, but you can do whatever you like. I mean, but that's the standard is suppose you have 100 data point, then you pick 10 split. Okay, and how the size? Okay, and you have to put how many observation in each node. Then it's going to be 5, 10, or 20. Okay. So I'm not going to run this code, but you can easily check this code is very simple. The only code important is this one. This line is this random forest regressor and the fit, right? Because this is creating a data. This is a split, which you have seen already. And this one, right? You're asking how many estimator you want each time, the control, the depth, how deep it is, okay? And you train it and test it. That's very simple, right? That's one line basically, right? One or 2 line, right? You can fit the X and Y, right? This can become a data, right? Just do it here, right? So random forest, nothing, right? Black box, one click, done, right? But I tell you somewhat about black box, right? What it's doing behind, right? It's just basically creating many universe and try to do that. Okay. And now Okay. And you can do the variable importance like this scope. I'm not going to do it, but there's something like that, but I'm not going to do that here. And there's something like a little bit complicated. I'm not going to talk about it, but it's technical part. Just what we call partial dependence plot is say trying to say if x changed by some value, how the y changes. Okay, it's more like the regression idea, right? Because you change x a little bit, right? How y would change. It's a partial derivative. Okay, it's kind of beta idea, right? How x changes to y changes, right? But this is non-linear, so it depends on where you are. X changes, how y changes. So the slope is not constant, right? Depend on where you are, how y changes. So this is what we mean by the partial dependence plot. Basically, it's just a regression, but the coefficient slope actually change according to where x is. Okay. So, but I'm not going to talk too much about this part because you will learn in detail in the machine learning class. So I don't want to overlap, right? Because there a lot of complaint, I think, from last cohort, and many courses are very similar. So now I try to avoid similarity. So machine learning, I try to not talk too much. Just give you some tastes of it, because some of you actually not going to take that class, right? Then I think applied business intelligence. That one is a machine learning class. I think next year they will change the name to call machine learning 1 and then machine learning 2. So they will change the name, but it's not, you don't know the name, right? It's like the black box class, but that one is the machine learning class. I mean, you want to learn, right? If you don't, I mean, it's okay. So let's apply, because I think that's the most important part, is to apply the model, right? To save time, allow me not to, I'm not going to copy and paste. Is that okay? I mean, to save time, because if you want, I can copy next class, but let me go over the code because quickly, because I think so what we're doing here is I have a random forest. I would tune based on I will go 33, bootstrapping 500 universe. Default, you don't need to change anything. And then you would try to number of variable is 8, 10, or 12. Why? Because square root of 500 is around 10. So you can say 9 or 11. Doesn't really matter anyway. Then minimum of, I forgot the number. I think I forgot that part. So this is the part that we have already. So I'm not going to run it. So this is the code, and you can check how many missing. And this is the part we have done last time. So I just basically skip. Okay, skip to here. Okay, just the before, just we have done in the previous class, right? Clean all the missing, all the thing. I'm not going to run that part. So and I have test string split, right? String size 70%, and then these are the variable that the main thing. Okay, and then these are the review amenity. We have seen that already. Remember. And the reviews, and then combine together, okay? And this is a interaction variable, and there's a predictor, okay? So random forest, as you would guess, is nothing new, okay? And the only thing that is probably that you may consider this is this guy, okay? Something interesting is how many cores you want to use to calculate random forest, because it is computation heavy. So use -1 means that everything. So that's important. Otherwise, you put 1 or 2 or 3, then probably you take forever. So no, and the estimated 30, right? We do it, right? And then here we use something important we call the grid search series, okay? As the way to figure out which model perform the best, okay? Actually, we talk about the LISO series, but LISO have automatically, so we just skip here. But I think the random forest, as a current moment, they don't have the freedom, okay? So the grid series is, grid search series is looking at you give me what are the parameter, look at the best, and then you fit it in. Okay, so we'll go slowly here. Okay, and here another one is called randomized search CV. Is the reason is why you have two different ways to do it. Now, we focus on this one. Okay, if the feature have 5, 7, or 9, speed is 6 or 11, which I said number of sample there. Okay, if this is a huge set, okay, doing one by one, your computer will take a very long time. Okay, so by randomized search means that I'm not going to look at everyone. Okay, I randomly pick up something, and that there's some way to figure out what is not, what is good. Okay, so how? Let me get a metaphor. Okay, suppose there's a girl here again. Okay, and I want to send her flowers, but I don't know what color. So what I'm do is I go the rainbow, right? Red, orange, yellow, green, whatever, right? Send all the color, right? See whether I got a favorable reply, right? I got a slap, right? Whatever. So then you try every single color, right? If that is all the flower, then it's easy, right? All the colors, that's fine. But not if you want to send her not just a flower, you also want to send her some other gift like handbags, right? You have to try LV, Coach, K-Spade, or whatever, right? Many different types, right? Many different color, right? Many style, right? A long stripe and a small one, a handbag, different type, right? There's many. Then you can't possibly look up everything, right? You try different combination and look for the best one. So that's smart way to look. Okay, it's the randomized search. Okay, so for our purpose, it's so simple. We can use it. We use the grid one. But when the thing is complicated, you will use the randomized. Okay, of course, when you randomize, it's not going to be best, right? Because you don't look at everything. Okay, that's the idea. Okay, so here we define the grid. The feature is 5, 7, 9, and the minimum speed is 11. Okay, so what we're going to do is call this function is called the grid search CV. Okay, you tell them which model you're fitting. Okay, we have is the random forest. Okay, of course you can use linear regression. You can use LISO, also fine. Okay, if you like this, is LISO also do it here. And you tell them what you're going to fit here. Okay, what is the parameter space over there? Okay, and CV means you try 5 different universe, right? You split the data into 5 times, right? 5 universe, train and test, right? Look at the lowest MSE. Okay, and then scoring there are many ways, but the easiest is use the mean square error. And you may ask, I have negative root minimum square error. The reason is the algorithm only know how to do maximization. Okay, so you maximize the negative, actually minimize. So that is the reason why the syntax is very weird. But anyway, I hope it's okay. I mean, they are doing maximization. So that's why the score is like this. Okay, because you want to minimize the RMSE, right? But the syntax is you have to maximize something. So that's why you want to maximize the minimum, the negative part. So I hope that's okay. Okay. And that's how you do it, right? You will try to look at the most complicated model, right? Because this is formula, predictor 2, right? Predictor 2 is the most complicated model. If you remember, predictor is like this one. Predictor 2 is this guy, this model, okay? And then you do the LRF random fit, you fit it, okay? Of course, it will be very computationally heavy if you try. Take a long time. So that's why I don't want to illustrate because I don't know whether the time to finish it. If I just wait, okay, maybe take a few minutes, 3 to 4 minutes to do it. Okay. Once you do it, you want to output the result because this model series has a lot of stuff. So we want to look at this 3 things: number parameter, minimum speed, and test score. Test score is the RMSE. Okay. Can you forget about this because this is same for everyone anyway. So this is the outcome. Okay, you will see. Okay, Here, actually not too much different, right? Depend on how many variable you want to feed, the RMSE is 30x something. Okay, so it's okay, right? No matter which one you pick, it's fine. Okay, so you fit 9 model there, right? That's the grid search, right? Because you do every single thing to search, right? To the nodes. Okay, and okay, and the question is, how to get the prediction, right? Because you're a prediction model, right? And why the model comes out like this, I don't know. Because you booster the data, you create different universe. Okay, and this comes out, you don't even see actually what universe you are creating. So how you get this model? No one know, right? I mean, of course, you can actually check the data, how it's being generated, but no one understands what's going on. Okay, the only drawback is, what's going on? I don't know. I mean, there's no formula there, right? Because even it's different from the case of regression tree. At least you can see, okay, this is a tree, how it follow this prediction. But this one is averaging out all this outcome, right? Averaging out this prediction of the random forest. So actually, it's not clear. Okay, what's going on? Okay, and as we said, you can do the partial dependence plot, right? Basically, change x a little bit, how y changes, right? You look at the coefficient, right? Because remember, that is basically telling us the regression coefficient in regression, right? If actually when you do the PDP is a flat or mini flat, you should just run regression, right? Why you do that, right? Because it's a stable, right? The only thing it allow, you can see from this, when you have random forest, you allow actually a regression that based on x, right? Different x, right? It's just basically, it's very similar to localized regression, right? Just you cut the data in a small part and run regression in this small part and connect together, right? So that is somewhat idea. But the good thing is, when this one, well, you can allow any shape of the model. You don't have to model. You can any whatever model you think is there. If the feature is there in the model, black random forest can capture it without knowing. And why you want to do that? Because this is useful when you have big amount of data, you don't know what to do, right? Completely have no idea, especially when you, that's why we learn this, because when you have internet data, there's huge data, have no idea what's going on. You don't even know, I mean, if you saw a pop-up, right, of a beautiful girl or a handsome boy, does it help? Right? How long they say there, can you help them to click? I don't know. Right? Or come a flash, right? You have no idea what's going on. Okay. So that is the reason why we need that there. Okay. And so these are all the variable importance plot, which are important, right? And this tells you if you plot everything there, it would be very complicated. And here I just do the cutoff, make the plot a little bit more easier, or put the top 10. Okay. And that would be the result there. Okay. So I'm not going to detail. Okay. But forget about GBM. I'm not going to cover it. Okay. So you can see, you compare the first 5 lines. OAS, as expected, is not very good. LISO is improved, reduction. And use regression tree actually is not as good as these two, right? Because it really depends on how complicated the model is, right? Because when your model have many useless stuff, the tree usually doesn't work very well, right? Because a lot of variable, tree doesn't work very well, okay? But if you go to random forest, actually do very well, right? Because single tree cannot capture everything. But you have different tree, you combine, can do a lot of stuff, because that's why different tree is going to be useful there. Okay. So, and you can see this is lowest. Okay. So it's just like the random, I mean, there's another method called the GBM, is the greatest boosting method. I don't want to forget about it. Just right? There's a boosting method, right? Basically, just like you grow the tree sequentially, and there's some method, okay? Use the gradient search to look for to build a model, because you can build a tree and build another one, right? Because remember, this method is in the first universe you build a tree, and second universe you build another tree, right? And how to build a tree is based on some gradient method, okay? That's how you do it, but I'm not going to talk about this. Too complicated to cover here. Okay? But I just did, that's why technical, okay? And the code is not complicated because the code is just this. So basically, that's why I put it here, because it's too easy to forget, right? Just and done, right? But if you want to run it, just run it, right? It's nothing new there, right? That's why the Python code just click and you go. So, but I just show you there's something here, but I don't want to go into detail. There's learning rate, right? There's a key point learning rate. But as I said, technical, so you can keep technical. But otherwise, other thing is very simple, right? So the only trouble is when you have GBM, this kind of stuff, it's so complicated. If you try to run it, okay, at least I think I try it at least like 15 minutes to run the code that I offer here. So I don't know. That's why I don't want to do it. Right. So, but you can see how long they take. ORS is just like less than, it's like 1 second, right? And then random forest already require 20 minutes. So that's why I didn't want to do in the class, right? You can't see the result. This one, look at how long it takes, right? It's a few days, right? So that means that unless you have nothing to do and your computer has nothing to do, okay, then you run this one, right? And the gain is very minimal, right? Random forest already pretty good, okay? Of course, random forest is already a long time already, right? So just a summary of what we have been doing. We've learned so many stuff so far, right? The main focus of this class, this whole course, is ORS, right? Which is the easiest, but you have the human hand to do everything, right? You have to select variable. You have to tell me whether you include square or not. Whether in the interaction is your own choice, right? And it's easy, right? You have the solution there. It's fast. The RMSE is okay, not too bad. And if you look at LISO is the change is how you select the solution is algorithm. And the solution is also algorithm because you don't know which one to pick, right? Because it depends on the alpha parameter you pick there. You can do CV, but this one is by algorithm, right? You don't know which one you pick, actually this one, but this is one way. And today we learned the tree. It's also very fast. But the problem is if you have a lot of features, then the tree doesn't look very well because they don't know which one to pick, right? Because you have hundreds of features and most of the features are not very useful. Then the tree cannot help a lot, right? Because if you have a lot of useless feature, the tree doesn't really help, okay? That's why tree, this one doesn't work very well, right? Although it's very fast because they use a greedy algorithm, remember, right? So look at which one reduce RMSE lowest, do it and keep doing that. It's minimizing each step, but not globally, right? They're not saying that I pick this tree, this tree, this tree, and I minimize it, right? So it's step-by-step minimization. So usually it's fast, but it's not good. So that's why the improvement comes in like this one, random forest, right? Where you actually, how can we do that? Is to randomly select the data, right? That's what the bootstrapping, right? And you grow the tree each and combine the tree, right? In that case, actually pretty good, right? Beat what we have learned, right? Of course, the cost is, I don't know how we compare this cost, right? If your life have nothing to do, your computer nothing to do, try it, right? No harm, right? 90 minutes, nothing, right? Just let the Google server run the thing, right? The problem, of course, is better. Everything is by algorithm. How to interpret? What's that? I don't know. You can run the PDP, right? Partial dependent point. You can see, but I mean, it's hard to say, right? Same as somewhere out of our syllabus, right? It's technical thing. It's GBM. There's some way to build a tree sequentially, right? But this is the problem is this is no way you can do, right? I don't know if you're happy to do that, but I'm not happy to do it, right? It's just like taking like 10 hours, right? More than 10 hours, right? Yeah, 10 hours a day to run that, right? So probably not fun, right? So I will make the assignment 3 on the last assignment, which you will be doing all 4 models. Have fun with that. Then you run it and you predict, compare the different model. Probably I would ask you to, I don't know whether hotel model can work, but probably I will use the same data set we use in the class, right? Use the Airbnb to do the last assignment, because only Airbnb have a lot of variable to look at. Okay. So that would be the very last thing we cover up until here. Okay. So although I just a little bit random forest, I just very scratch the surface. The reason is if I want to cover anything more difficult, then it's very time consuming to do it. So and then you will see the next class, the only very last class for my part, right? You still have this class goes on, will be lesson 9 and lesson 10. So although a lot, but I will just to give you some idea what's going on to calculate causal inference. Okay, tell you that when the main thing is next class is when we will tell you to do the causal map. Okay, which means that if I try to look at whether X cause Y, it's different from running regression prediction. Means that we have to decide what should be in X and what shouldn't be X based on our theory. Okay, because in prediction, I don't care. Just the thing that helps us predict, I can put there. I don't really care whatever. Okay, as long as it reduces my RMSE, I'm done. But when you try to discover causality, you have to be very careful what should be there and what shouldn't be there. It's not driven by RMSE. It's driven by our domain knowledge, driven by how we think how things work, what assumptions we make. Okay, so that is the causal map we will talk about in more detail. And then I think we can't cover so many things, but I think we skip the some of the material, especially 21, and probably we will spend time on the very last idea. Lesson 10 will cover the main thing is called different difference. I think we spend most of time on this one because this is predominantly the most common framework when you cover causality. Different is simply when you do experiment, control group and treatment group. Say you want to see the medicine, whether it work, you give the medicine to one guy, you give the placebo to the guy, and see whether there's a treatment there. Okay, but this is the thing before and after control and treatment. So this is the most important, and probably the rest I will just have no time to cover. We just I think it's okay. I skip. But do remember, next class onward will be just telling you, not in the exam. So if you want to prepare exam up until today, it'll be okay. Okay. I will see you next week. I hope. Happy weekend.